Okay, using Gibbs equation, ice does not melt at low temp. So with the Gibbs equation, we've got delta G is equal to delta H minus temperature delta S. So how would you explain this? So we're trying to melt ice. So talk about that for a second. I'm trying to melt it. What would I need to do to melt it? So to do this, to melt ice, what would I have to do to the enthalpy of the water that's solid? I'd have to increase the amount of energy that the water has as a solid, right? And when ice goes from being a solid into the liquid state, what happens to the entropy? Entropy goes up. So talk about the fact that both of these things are going up. Good, bad, both. Good, both. By good, I mean nature. Is nature happy with this? Wishy-washy? Not happy, right? Happy. Okay, so if it turned into a liquid, nature would be happy with that because its entropy went up. It became more disordered. But to make it a liquid, I have to put energy into it. And nature's not happy with that. So if I were to increase this and I were to increase this, how do I make this a negative value? The temp has to what? This is a term and this is a term, right? To make this a negative value, what do I need to do? This term over here would have to be bigger, right? Because this delta H is going up, so that would be a positive value. So that would be working against nature. So what if the way I can change this to being bigger or smaller is by modifying the temperature, right? So if the temp is low, tell me about this term.
Small.
It's small. So at a low temp, the fact that I'm changing the enthalpy entropy isn't good enough, isn't enough. That change in enthalpy is too large for that change in entropy to overcome. Okay, so we know what these hand warmers we're talking about here.
Standard hand warmers?
Standard? Probably. Just assumed everybody knew what I was talking about or looked it up. Oh, these guys? All right, so let's go back over here. So explain why the hand warmers are negative delta G.
Negative means you give off energy.
So,
Heat. That's first.
what's the so we know what the delta H is, right? Is everybody okay with? I mean, it's exothermic. You know that because heat's given off. So that means the delta H is a negative value. Are we okay with that? So talk to me about the delta S. It's a positive value. So what is inside that hand warmer? Really? Nobody looked it up? Iron. Fe solid powder. What's the other reactant? Oxygen from the atmosphere. What are you doing? And the result? What does it look like? Has anybody seen one broken open? No? What do you think the result of mixing iron with oxygen is? It is rust. It's Fe2O3 solid, which is iron 3 oxide, which is regular rust. So if you let one of those things burn itself out, you crack it open, it just looks like rusty iron because it's rusty iron. So tell me about the delta S. Why would it go down? If a solid and a gas turns into a solid, so maybe you might think that, but what's more important than the fact that the state changed? The iron is not by itself now, and the O2 is not by itself now. I took two things that were segregated, that were little concentrations onto their own, a package filled with just iron atoms, and then I put oxygen in there and bound them up. So now I basically have mixed those things together. So then my delta S goes up. So when is this a spontaneous reaction? Always, right? It's always a spontaneous reaction because it's giving off heat and it's increasing its disorder.
Is there any way to check iron things to make them?
Anybody? How do we do that? How do we protect iron from rusting? That's really what her question is. I paint it. Anything else? Say again? That is a possibility. You could let the exterior rust, and as long as the thing that you let rust isn't physically agitated, the rest of the iron is going to be totally fine. The reason that you have like a rusty spot on a car, and it's much better to like sand that off and repaint it than just let it stay, is the car is agitated. So that rust falls off and then exposes more iron underneath, and then the rusting process can continue. But if there was no removal of the rust on the exterior, then it wouldn't be a big deal. What's the other? I paint it. I could let it sit there and not mess around with it. One other way. What's your silverware made out of at your house? Don't say plastic. What is stainless steel? Mm-hmm. So you can take that iron and mix it with other metals, or in this case, if it's steel, it's carbon, and then its properties change. And the property is that it takes a higher temperature and more oxygen to rust it. So somebody had silverware rust, forks and knives or something like that. It's older stuff usually when people were trying to get really chintzy with making the metal.
That's right, polished.
It'd say, well, no, that's silver. That's a different situation. They would say that this is not dishwasher safe stuff. So what they made is really, really crappy steel. And so making that stuff has become so inexpensive that you really can't find it anywhere where it says it's not dishwasher safe anymore. Like if you go into Fred Meyer's and they're selling a full silverware set for like $10, that'll probably rust in the dishwasher. But everything else most likely will not. So why did dead things disappear? You okay with that? Solid stuff's going to turn into liquid stuff. Might turn directly into a gas, but eventually it'll turn into a gas and it disappears because it's a different state and floats away. And entropy increases every time I do one of those things. So ultimately that's going to win out. Okay, so we've got 62 degrees Fahrenheit. That wasn't very nice. So 62
289.
times 5 ninths minus 32. Did I get that backwards? Yeah, let's see. 62 times 5 divided by 9 equals minus 32 equals, something's wrong there. 62 minus 32 times 5 divided by 9. Yay. Erase. Minus 32 times 5 divided by 9, I get 16.7 plus 273. Let's go with 290. Okay. So what else do I want to do? Yeah, this kilojoules and this joules, that's going to be a problem for us. So I'm going to take this and turn this into negative 2200 joules per mole. Okay, so my delta G is equal to negative 2200 joules per mole minus 290 K times 9 joules per mole K. And so then my K's cancel out. Get negative 2200 minus 290 times 9. Negative 4810 joules per mole. Is it spontaneous? Sure. Could you have answered this question without doing any math? Yes. Right. Because my S was a positive value and my delta H was a negative value, so automatically that means it's got to be spontaneous.
Well, would you be offended if I go up to the board and erase those two ones?
Nope. It's bugging you that bad?
Not yet, it is. Okay, I'm good.
Thanks. Okay, so what do we want to do with this last problem? What do you need to do? We're using so we needed to find the delta H's for the reactants and products and the delta S's for the reactants and the products. So let's is it, I feel like it's in here though. Was it in here? I think I actually need to open up the full book, don't I? Is it appendix I? G? There we go. That's irritating. Does anybody have the book? So I'm sorry, what do we need?
H's and S's.
H's and S's. For what elements, sorry, substances? Calcium carbonate. CO2? Okay. So we got negative 390, I'll just say 4, and 213, or 214. And then, what else? Calcium carbonate? Is it really not here? Oh yeah, there it is, sorry. Negative 0 and 110. And then is it calcium oxide? Is the other one?
Yeah.
Negative 634 and or 635 and 38. 38. So SH CaO CaCO3 CO2. All right. Bless you. All right, so my delta H, my products for my delta H are, so negative 635 plus, oops, negative 394 minus negative 1200. And my delta S is 214 plus 38 minus 110. Negative 23. 35 plus negative 394 plus 1200. So this is 191. And down here we've got 214 plus 38 minus 110. Here we've got 142. Were those, it was kilojoules and joules? Is that right? Kilojoules and joules. So this one is kilojoules per mole. This one is joules per mole. Is there any issue with this so far? What is it? Any other issue? It's a gaining energy, right? The enthalpy is going up. So nature doesn't want that. But the disorder is going up. So these two things are fighting each other, right? So what didn't I give you that you should be able to figure out? What was the temperature? Yeah, so what are we using? Say again? It's going to tell you on whatever table that you're using. Yeah.
On that, on the enthalpy, it says in Fahrenheit, is that right?
What?
So if that's what the F is. In that table. Over on the H, there's an F, and I assume that meant Fahrenheit, is that what you
Formation.
mean?
It means something else. There's no temperature unit associated with enthalpy. It's just kilojoule, or it's just energy in moles. So then my delta G is equal to 191. Well, let's do this. I'll do, no. Is that enough? Barely. That's joules per mole. And then I'm going to subtract off 298K and then 142 joules per mole K. K's cancel out. So let's see what happens here. 1910 minus 298 times 142. Oh, huge. Great. So I got delta G equal to negative 40.4 kilojoules per mole. Okay, so spontaneous or non-spontaneous? Yeah. I say kilojoules. Oh, I'm sorry. You mean this? Yeah, you're right. There should be 2 more zeros there. That's seriously bad. Oh, well, that totally changes everything. So if I put 2 more zeros here, and then I do the math again, I get 149 kilojoules per mole.
Wait, kilojoules or
Kilojoules. So non-spontaneous? You go with that?